turns out that there's a direct relationship between solution temperature and solubility. That is, as the solution temperature increases, so does the solubility. And as solutions get colder, solubility tends to decrease. We can rationalize that by this statement here, which is actually two statements in one. I'll go ahead and read it twice. First with the uppercase bold-faced words used, and then with the italicized and underlined words used. Increased kinetic energy makes for the solvent molecules being able to dissolve out and keep suspended more ions. Or, decreased kinetic energy makes for the solvent molecules being able to dissolve out and keep suspended fewer ions. Solubility is directly related to temperature. Another factor that affects the solubility of insolubles is the adding or removing of common ions. To help you figure out what's going to happen to solubility, you want to keep in mind Le Chatelier's principle here. For example, for this equilibrium system, solid calcium fluoride in equilibrium with calcium ions and fluoride ions, if we add calcium ions or fluoride ions by adding some sort of strong electrolyte like calcium chloride or sodium fluoride, the system will want to shift to the left, and if the system shifts left, then the solubility will decrease, because when we're talking solubility, we're dealing with the amount of the solid that is not dissolved or that is dissolved in the solution. So the solubility will decrease. Similarly, if we somehow were able to remove calcium ions or fluoride ions, again, Le Chatelier would tell us what to do. He would say that we're going to shift to the right, and if we shift to the right, that means the solubility of this calcium fluoride has increased. Thirdly, the solubility of some compounds, most notably ones that have anions that act as bases, is affected by pH changes. Let's consider this compound, iron 2 hydroxide. It is an insoluble salt, but there are a small number of iron 2 and hydroxide ions that will dissolve out into the solution. Our Ksp expression would look like that. Visually, what we have here is in the upper right corner, we've got a beaker, and in the bottom of the beaker we have the solid compound. Then the beaker is filled with water to a certain level, and there are a few iron 2 ions and a few hydroxide ions floating around in the solution. If we acidify the solution, in other words, if we dump some hydrogen ion in, won't the hydrogen ion react with the free hydroxide, causing the concentration of that hydroxide to decrease? And Le Chatelier would say, if the hydroxide ion concentration decreases, we should shift to the right in this equation, and if we shift to the right, then more of the iron 2 hydroxide solid will be dissolving out. On the other hand, if we somehow increase the pH, that is, make the solution more basic, that means that the hydroxide ion concentration will have increased, and again, per Le Chatelier, if the OH ion concentration increases, we're going to want to shift this system to the left, and that will mean that the solubility of the iron 2 hydroxide will have decreased. Other anions besides OH minus that would behave similarly are these. Not coincidentally, all of these are the conjugate bases of weak acids. Let's summarize. In this lesson, we discussed three factors that affect the solubility of a solid. 1. Solubility is directly related to temperature. The greater the kinetic energy of solvent molecules, the more ions the solvent can free up and keep suspended in solution. 2. The addition of common ions to the equilibrium system of an insoluble decreases solubility. And 3. The solubility of compounds having anions that act as bases is affected by pH changes. Notably, as the solution is acidified, the basic anions react out of solution, and so more insoluble dissolves out of the solid form in an attempt to replenish.